Today we are here with the last module of this chapter, that is module 4, which is electric flux and Gauss's theorem. So what is electric flux? Let's discuss. Here we can see electric flux. Okay, what is this electric flux? Watch here. This is a surface which is placed in the electric field. These are the electric field lines in which this surface is placed. So the number of electric field lines, the number of electric field lines which are associated with this surface is called electric flux. We can say that the number of electric field lines associated with a surface is called electric flux. Okay, now one more thing, watch here. We can watch this surface here and a vector which is perpendicular to the surface like this. A vector which is perpendicular to the surface is called area vector, is represented as A. This is called area vector. An area vector is the vector which is perpendicular to the surface area. Moving ahead with some more about electric flux. Watch here. This is the surface we have considered which is tilted at an angle theta. Due to this tilt, the angle between the electric field and the area vector is theta. Okay, so these are the factors: the electric field, the area vector, and the angle between the area vector and electric field is theta. So the electric field associated with this surface will be given as like this: phi is equal to Ea cos theta, where phi is equal to electric flux, A is equal to the surface area, theta is the angle between the area vector and the direction of the electric field, and E is the electric field. Moving ahead, watch here. This is phi is equal to Ea cos theta. It is clearly representing that phi is the scalar product of vector E and vector A, because here we can see cos theta. So we can write it like phi is equal to vector E dot vector A. So we can say that the electric flux is a scalar quantity because it is the scalar product of the electric field and the area vector. It is represented as phi, you can see here, and its unit is Newton meter square per coulomb or voltmeter. We can find the unit from this formula. Now moving ahead to the Gauss's theorem, let's discuss. Let us consider a surface which is enclosing a charge Q. Then the Gauss's theorem states that the electric flux associated with a surface is 1 upon epsilon naught times the charge enclosed by the surface. If we want to find the electric flux associated with this surface, what we need to do? We need to take 1 upon epsilon naught times the charge, the Q, enclosed by the surface. That is phi. Electric flux is 1 upon epsilon naught times the charge enclosed by this surface, or we can write it like phi is equal to Q upon epsilon naught. This Q comes here and becomes phi is equal to Q upon epsilon naught. This is the expression for the Gauss's theorem. Now we need to prove this. How to prove? Let's see. Here is the proof of this. Let us consider a surface at the center of which the charge Q is placed. The radius of this sphere is R, and we have considered a small portion of the surface which is dA. The area vector associated with this small surface is dA, and the direction of the electric field is parallel with the direction of the area vector. So watch here. The electric field due to the charge Q at the distance R. Due to this charge Q, we will find out the electric field here, which is at a distance R. So this will be E is equal to 1 upon 4 pi epsilon naught q upon r square, as we have discussed in case of the electric field due to a point charge. Now, the electric field associated with the surface dA, this surface dA, the electric flux associated, we have to find out the electric flux associated with this small surface dA. The electric flux associated with this small surface will be given as this: d phi is equal to EDA cos theta. As we know, the formula for phi is equal to EA cos theta. But if the surface is small, if we need to find out the electric flux associated with this small surface, then we need to take the flux which is d phi, the small flux d phi, which will be given as d phi is equal to EDA cos theta. Now what we need to do, we need to put the value of E from the equation 1. So now putting the value of E from equation 1, what happens? Let's see. We have put the value of E, which is 1 upon 4 pi epsilon naught q upon r square, and dA as it is, cos theta as it is. Now watch here. Here you can watch the direction of the area vector, the direction of the area vector and the direction of the electric field. Both are same, or we can say both are parallel. When these both are parallel, the angle between the electric field and the area vector will be 0. So we can see here theta is equal to 0. Therefore, put the value of theta as 0, we get this. So it becomes d phi is equal to 1 upon 4 pi epsilon naught q upon r square into dA cos 0. Put the value of cos 0, that is 1. So it becomes like this: d phi is equal to 1 upon 4 pi epsilon naught q upon r square into dA. Now we will integrate both the sides. Integrating both the sides, we get what we get. Let's see. Integrate this side and integrate this side. Watch here. 1 upon 4 pi epsilon naught, it is a constant. Q is the charge placed at the center, it is also constant. R is the radius of this sphere, which is also constant. Here, or wherever, the R is constant. So we will integrate just this dA. So this integration sign comes here. We don't integrate these constants. What happens next? Watch here. dA, we are integrating dA. dA is the small part of this whole surface area. If we integrate this small part, we get the whole part. The whole part which is the surface area, of this sphere, which will be 4 pi r square. The surface area of the sphere will be 4 pi r square. So we will put the value of integration dA as 4 pi r square. Now put this here. The integration dA we have put as 4 pi r square, and integration of d phi becomes just phi. Now watch here. This r square will be cancelled out by that r square. This 4 pi will be cancelled out by that 4 pi, and we will get just these quantities, which will be q and this epsilon naught. So here we have phi is equal to q upon epsilon naught, and which is the expression for the Gauss's theorem that we needed to prove. This is the final expression for the Gauss's theorem. Okay, moving ahead with the applications of the Gauss's theorem. What are these applications? Here are the applications. Electric field, we need to find the electric field with the help of Gauss's theorem due to an infinity long straight wire. We also need to find out the electric field due to uniformly charged infinite plane sheet, and also we need to find out the electric field due to uniformly charged thin spherical shell inside and outside the shell. All these applications we are going to do with the help of Gauss's theorem. So let's discuss them one by one. So here we have our first application of Gauss's theorem, which is electric field due to infinitely long straight wire. Let us consider an infinitely long straight wire on which the charge plus q is uniformly distributed. we need to find out the electric field at a distance r from this straight wire. So what we need to do, we have to assume a Gaussian surface around this conductor wire. What will be the Gaussian surface? It would be like a cylinder, like this. Here, this is the Gaussian surface we have assumed about this long straight wire. In case of applications of the Gauss theorem, we always assume a Gaussian surface. So watch here. This surface, the area vector associated with this surface will be like this, perpendicular to the area, which will be in this direction, and the electric field is away from the positive charge like this, which is parallel to the area vector, and hereby the angle between this electric field and this area vector is 0, and the value of cos 0 becomes 1. Now talk about this area. If we talk about this area, the area vector will be perpendicular to this, and the area vector perpendicular to this surface will be perpendicular to the electric field also. This area vector will be perpendicular to the electric field, and hereby theta becomes 90 and cos 90 is 0. If cos 90 is 0, then the flux associated is also 0, because phi is equal to Ea cos theta. If we talk about this surface, the angle between area vector and electric field is 90. Hereby the flux associated with this surface and with this surface will be 0, because theta for this surface and this surface is 90. Hereby we ignore these surfaces because the electric flux for these surfaces is 0. So we will consider only this surface. Okay, now what we need to do, we have to apply the Gauss theorem and the definition of the electric flux. Let's see. According to Gauss theorem, we know that phi is equal to q upon epsilon naught, and from the definition of electric flux, we have phi is equal to E integration dA cos theta. Now from equation 1 and 2, we will equate these values of phi. We will get this. From equations 1 and 2, we get E integration dA cos theta is equal to q upon epsilon naught. Now we will apply the conditions. Here theta is equal to 0. We are talking about this surface. For this surface, theta is 0 because the angle between the area vector and the electric field is 0. And this surface, we are taking here the small portion of this surface, which is dA. If we integrate this small portion, we get the whole portion, and the whole portion of this cylinder is 2 pi rl. 2 pi r into height. The height is we have considered as L. So this will be 2 pi rl. Now we will put these values of integration dA and theta in this equation. So what happens? Let's see. Therefore, E as it is, the value of integration dA we have taken as 2 pi rl, cos as it is, the value of theta is 0, q upon epsilon naught as it is. Now we will put the value of cos 0 as 1. So this becomes E into 2 pi rl is equal to q upon epsilon naught. Now we need to find out the value of electric field. So take all these factors to that side. What happens? This happens. E is here. This 2 pi rl goes there and combines with this epsilon naught. 2 pi with this epsilon naught becomes 2 pi epsilon naught, and this rl in the upon of q becomes q upon rl. Okay, we have discussed about the constant which was 1 upon 4 pi epsilon naught, but here we can see 1 upon 2 pi epsilon naught. We can make it 1 upon 4 pi epsilon naught by multiplying and dividing by 2. How? Like this. This becomes 1 upon 4 pi epsilon naught, but we need it to multiply with 2, and this r comes in the upon of 2, and this q upon l we are taking here. Watch this Q upon L. This is the charge upon length. We have read about some charge densities. Q upon L. Q upon L was the linear charge density, which we represent with lambda. Q upon L is the charge present per unit length, which is termed as linear charge density and denoted as lambda. So we can put this Q upon L as lambda right here. E is equal to 1 upon 4 pi epsilon naught as it is, 2 upon r, as it is, and this Q upon L becomes lambda. Lambda is the linear charge density. So this is the expression for the electric field due to infinitely long straight wire, which is an application of the Gauss's theorem. So moving ahead with some more applications here. Electric field due to uniformly charged infinite plane sheet. Let us consider an infinite plane sheet on which the charge plus q is uniformly distributed. We need to find out the electric field at a distance r from the sheet. So what we need to do? We need to assume a Gaussian surface which encloses these charges like this. This is a Gaussian surface we have assumed here, which is a cylinder passing across this infinite sheet. Watch here. We have taken the area vector dA, which is perpendicular to this, and the electric field, which is away from the positive charge, is in the direction of the area vector. If we talk about this area, then the area vector dA is perpendicular to the surface, and the electric field, which is away from the positive charge, is again parallel to the area vector. Here in this case, the electric field and area vector are in the same direction. Theta is 0. We'll consider here electric field and the area vector are in the same direction. The angle is 0. We will consider the electric flux. But if we take this surface, this surface, the area vector for it will be like this, which will be perpendicular to the electric field, and we will ignore this. Why we ignore? Because the angle becomes 90 for this surface. For this surface area vector, the area vector of this surface is perpendicular to the electric field. That's why we ignore this. We take only this surface and this surface. So there are two surfaces, so the electric flux will be doubled. Now applying the Gauss's theorem. We have phi is equal to q upon epsilon naught, and from the definition of the electric flux, we have phi is equal to 2 times E integration dA cos theta. Why 2 times? Because we can see here, once the electric flux, this one, E integration dA cos theta, and another electric flux, E dA integration cos theta for this surface. So we have phi is equal to 2 times E integration dA cos theta. From these equations 1 and 2, we will equate the values of phi and we will get this. From equations 1 and 2, we get 2 times E integration dA cos theta is equal to q upon epsilon naught. Now we will apply the conditions here. Here theta is equal to 0, as we have discussed in this case, and in this case theta is 0, and the integration dA, we have assumed this cross sectional area as A. So if we are taking the small portion dA, then we integrate that, then we get the complete portion, which is A we have considered. So integration dA is equal to A. Now put these values in this equation, we get this. 2 times E as it is, integration dA becomes A, cos theta becomes cos 0 is equal to q upon epsilon naught as it is. Now put the value of cos 0 as 1, we get this. 2 into EA is equal to q upon epsilon naught. We need to calculate the value of E, so take this 2 and A to that side. So this becomes E is equal to 1 upon 2 epsilon naught. This 2 joins this epsilon naught, becomes 1 upon 2 epsilon naught, and this q takes this a in the denominator and becomes q upon a. Watch here, q upon a, the charge per unit area. This is what? The surface charge density. Q upon A is termed as surface charge density, which is represented as sigma. So we can write it like this: 1 upon 2 epsilon naught. As it is, Q upon A we are taking as sigma. So we can also write it like E is equal to sigma upon 2 epsilon naught. This is the expression for the electric field due to uniformly charged infinite plane sheet. Moving ahead with the next application, which is electric field due to uniformly charged spherical shell. So in the case 1, we need to find out the electric field at a point which is outside the shell. So let us consider the shell, this shell, which is having the charge plus q all over distributed on this surface of the sphere. And we need to calculate the electric field at a distance r from the center of the spherical shell. This r is higher than the radius, that's why the point P is outside the sphere. In this case, we are taking a point outside the shell. So this P is outside this sphere, this spherical shell, outside the spherical shell. So we need to calculate the electric field at the point P, which is outside the electric shell, spherical electrical shell. So how to find out? We again need to assume a Gaussian surface around this, taking r as the radius, and we are taking a Gaussian surface which is also a sphere and having a radius r, small r. This is the Gaussian surface we are assuming here. Wherever we need to find out the electric field passing through that, we assume the Gaussian surface. So here we need to find out the electric field at the point P. That's why we have assumed the Gaussian surface going through P. Now what we need to do? We need to apply the Gauss's theorem with the definition of electric flux. As we know that this is from the definition of electric flux and this is from the Gauss's theorem. We have applied this directly. E integration dA cos theta is equal to q upon epsilon naught. Now we need to apply the conditions. The direction of the electric field and the direction of the area vector will be parallel to each other, because this direction of electric field is perpendicular to the surface and the direction of area vector is also perpendicular to the surface. That's why we will take theta as 0. And this integration dA, watch here, the small surface of this big sphere is dA. When we integrate this small part of this surface, we get the whole part, which is the total surface area of this Gaussian surface, and the total surface area of this Gaussian surface or the spherical Gaussian surface will be 4 pi r square, 4 pi small r square. We take the radius of the Gaussian surface. So let's apply the conditions. It becomes theta is 0 and integration dA is equal to 4 pi r square. Put these values in this equation. What we get? We get this. E as it is, integration dA we are putting like 4 pi r square, and cos theta we are taking as cos 0, and q upon epsilon naught as it is q upon epsilon naught. Now we will solve this. Put the value of cos 0 as 1. This becomes E into 4 pi r square is equal to q upon epsilon naught. Take this 4 pi r square to this side. What we get? We get this. E is equal to 1 upon 4 pi epsilon naught q upon r square. So this is the electric field due to a uniformly charged spherical shell at a point which is outside the shell, which is P. So this is the expression for the electric field at a point outside the shell. Now we will find out if the point is on the shell. Watch here. If we are considering at a point on the surface of the shell, watch here, this P is outside the surface. If we take this P on the surface, then what happens? This small r is equal to the capital R. when this P comes to the surface, then this small r will be equal to the capital R. So what we need to do in this case, we need to just put r is equal to capital R. So what happens? It becomes E is equal to 4 pi epsilon naught Q upon capital R square. This is the expression for the electric field due to uniformly charged spherical shell when the point is on the surface of the spherical shell. One more case we have, that is at a point inside the surface. Watch here. Let us consider this is the spherical conductor shell which is having the radius capital R and a center O. We have to find out the electric field at a point P which is inside the conductor shell, and at a distance small r from the center of the sphere. So what we need to do, we need to assume a Gaussian surface through this point P where we need to find out the electric field. Let's assume the Gaussian surface. It would be like this. This is the Gaussian surface we have assumed, and we have to take the surface area of this Gaussian surface in the calculations. So apply the relation. We know that E integration dA cos theta is equal to Q upon epsilon naught. This is from the definition of electric flux, and this is from the Gauss' theorem. We have combined them to make a relation. So what we need to do, we have to apply the conditions of the area vector and electric field, which is like always 0, and integration dA is equal to 4 pi r square. We are taking the total surface area of this small sphere, which is the Gaussian surface, Gaussian spherical surface. Okay, now put these values in this equation. What we get this E into 4 pi r square cos 0 is equal to Q upon epsilon naught. Put the value of cos 0 as 1. We get this E into 4 pi r square is equal to Q upon epsilon naught. Here one thing we need to consider, one thing we need to memorize or be taken into consideration, that if we are taking a conductor shell, then all the charge remains on the surface of the conductor. In case of a conductor, all the charge remains on the surface. At the inside of this spherical shell, the charge will be 0 because it is a conductor, and a conductor has all the charge on its surface. So all the charge remains on the surface on a conductor. That's why in case of inside, so the charge inside Q is equal to 0. When the charge inside Q is equal to 0, put the value of Q in this equation. What we get? We get E into 4 pi r square is equal to 0, as we have put the value of Q as 0, and hereby E is also 0. So in case of a conductor shell, the electric field inside the surface of the spherical shell will be 0, because inside the charge is 0, as all the charge of a conductor remains on the surface. So the electric field inside the surface of a uniformly charged spherical shell will be 0. So these were the 3 applications of the Gauss' theorem. Now one more thing is here, which is electrostatic shielding. Watch here. This is a conductor shell which is having the electric field around it, but inside the electric field will be 0, as we have calculated in the previous case. The electric field inside is 0 because the charge inside is the 0, because a conductor shell has all the charge on its surface. So if we put something inside this sphere, then that object will be prevented from the electric field and will be having an electrostatic shielding. This will work as a shield for that object where the electric field is 0, and around that the electric field is of a value, and inside the electric field is 0. So if we put an object inside this shell we will say that the object is electrostatic shielded. So what is this? It is the process of isolating a certain region of space from external field, like this. This is a certain region which is isolated from this electric field. Why this is isolated? Because it is a conductor and all the charge remains on the surface of a conductor. It is based on the fact that electric field inside a conductor is zero. So with the help of this fact, we have isolated an object, and this process is called electrostatic shielding. So thank you for now. See you again.